Good evening everyone and good evening to you, Mr. Cueto. We are the group 4 and we are here to discuss the stall warnings. Stall warning signs are the parts or system that alert the pilot that the aircraft is about to stall. It is crucial because the pilot will take steps to prevent a full stall, which might result in an incident or accident. So, stick shaker. The aircraft's stall protection system, which is made up of wing-mounted angle of attack sensors coupled to an avionics computer, includes the stick shaker. The angle of attack sensors and a number of other flying systems provide data to the computer. The computer activates both the stick shaker and an aural action or indication when the data suggests an impending stall issue.
Regulations stipulate that in large aeroplanes, the stall warning system must activate before the stall speed by an amount greater than either 5 knots or 5% of calibrated airspeed. It must continue to work until the angle of attack is reduced to at least the point where the stall warning was initiated. The warnings can be in the form of visual warnings, sensory warnings, such as stick shakers, which are fitted to the majority of traditional type aeroplanes, and audible warnings. Store, store, store. Most aeroplanes tend to use a combination of these indications, and more modern aeroplanes use the visual and audio indications as their stall warning system. Store, store, store. We now move on to the stall protection system. The basic difference between this and the stall warning system is that at the onset of stall protection, providing it has not been isolated, it cannot be overridden, whereas a stall warning system can be. In traditional aeroplanes, stall protection takes the form of a stick push, which physically moves the control column forward, initiating a reduction in the angle of attack. If we look at this graph for a typical fly-by-wire aeroplane, its protection starts at alpha protection, where alpha is the angle of attack. At this point, even if the pilot is demanding full-up elevator, the system will only provide a proportion of the actual demand. As alpha continues to increase and reaches alpha floor, the thrust levers are selected to take-off go-around thrust to safeguard the aeroplane. We are now going to look at the typical components required for a stall warning protection system to function. If we look at the inputs required, we need to know the angle of attack, which is provided by a sensor, which we will be looking at in more detail in the next part of this lesson. The positions of flaps and slats affect the pitch of the aeroplane, and therefore the system requires that information. Airspeed is another requirement, and is supplied from the air data computer. The amount of power on the aircraft is also a factor, as the power on stall speed is higher than the power off stall speed. The stall warning system is inhibited on the ground, and so we need an input from the weight on wheels microswitch. We will now look at the outputs from the stall warning module, and as already stated, aeroplanes will have a combination of indications. First is the stick shaker motor, which is fitted to more traditional aeroplanes. Then we have visual warnings, which come as master warning lights, and written warnings on electronic screens, and audible warnings in the form of synthetic voices and oral warnings. We also have an output to the angle of attack indicator. There is also a test facility, which can only be used on the ground to test the system.
So yung stall warning signs is yung part ng system na nag-a-alert sa pilot na yung aircraft is nakakaranas ng stall. Nagiging crucial siya para sa pilot dahil gagawa niya ng paraan ito para maiwasan yung mga pwedeng result, which is accident. So para malaman yung stall warning, merong device aircraft na nag-horn para malaman ng pilot na nakakaranas na ng stall yung aircraft. A stall occurs when the angle of attack exceeds the value which creates maximum lift as a consequence of airflow of it.
So, let's move to sensory cues for pilot. The first one is feel. The second one is hearing. The third one is vision. And last but not the least is kinesthetics.
Vision is to perceive. Flight is particularly demanding for our visual sense, as it is not adapted to the high speed and three-dimensional movement involved in flying. Make it susceptible to illusions, particularly at night, in poor light, or in conditions with few external visual cues. Vision is the most important for safe flight. Starting out, obviously, we need to be able to see where we're going, look out for other aircraft, keep an eye out for terrain and obstacle, and judge and determine our altitude and distance based off visual reference to keep us safe. It is also important when there is impending stall, we know what we do for pilot. Kinesthesia is a sensation. It is awareness of the position and movement, a physical sensation, sometimes referred to as seat of the pants sensation. In most normal earthbound activities, when combined with sight and hearing, this can be fully relied on to help us perceive the world accurately. If this sensitivity is properly developed, it can warn the pilot of an impending stall. Kinesthesia is an important indicator to train and experienced pilot in visual flight. If this sensitivity is properly developed, it can warn the pilot of an impending stall. It can also be called muscle memory.
It has been a smooth flight. The aircraft is on final approach and about to reach Category 1 ILS, decision height of 200 feet in instrument meteorological conditions. The captain is flying. His co-pilot is looking at the instruments and at 300 feet calls 100 above. At 200 feet, the co-pilot calls decide. The captain responds with go around, sets toga thrust and begins to pitch up. Contrary to SOPs, he looks outside but has no visual references and consequently perceives the acceleration as a false pitch attitude. Due to this somatographic illusion, the captain applies stick down, quite the opposite of the movement that's required. As the pitch down continues, the aircraft starts descending instead of climbing. Earlier in the cockpit, the co-pilot stayed on the instruments and saw the pitch attitude reducing, the airspeed increasing, and he called out, pitch. The captain only hesitantly responded, and the aircraft continued to lose height. Almost at the same time, don't sink sounded due to height loss. This supported the captain's acceptance of the co-pilot's call, and collision with the ground was averted. Accident and serious incident investigations have shown that collision with terrain is likely if the pilot flying is affected by sensory illusion and fails to respond to the pilot monitoring alert. For go-around, pilots need to react timely and with precision. Toga thrust, adapt or change configuration for the missed approach, and once positive climb is confirmed and called, gear up. Both pilots should fully rely on their flight instruments throughout the approach and go-around. But it's absolutely critical that the pilot monitoring always stays on instruments and does not delay an alert call-out if the pilot flying fails to maintain go-around pitch attitude. Disorientation caused by sensory illusion should then be primarily a risk for the pilot flying only. Spatial disorientation can occur as any go-around begins, particularly if it is unexpected. So keep in mind the following key messages. When initiating a go-around, the sudden change from low to high thrust can create sensory illusions. The flight instrument display of aircraft attitude is the only reliable reference available for a go-around in all conditions. During a go-around, the pilot flying must prioritize the required pitch attitude from the attitude indicator. The pilot monitoring is the last barrier if one pilot looks out and is affected by sensory illusion. But the real defense is head in, not head out, for both pilots at the beginning and throughout any go-around. Learn more about sensory illusions on Skybury.